Let's get going. So today we're going to start to talk about model-free prediction. So what that means is taking something like an environment that could be represented by a Markov decision process, but no one gives us the MDP, and we still want to solve it. And so I think up to this point you should be wondering, correctly, well, this is all very well, but what if I don't know the exact equations governing the way in which my factory operates? What if no one tells me, how the pollution level which comes out of the smokestack really depends on the torque which I put into the engine and so forth? What do you do in those situations? And the answer will be we'll start to understand that in this class, where we'll talk about model-free prediction. So methods for which no one tells us the environment, and the agent still has to try and figure out the optimal way to behave. So we're just going to start by introducing the basic ideas. And then there's going to be two major classes to model-free prediction that we're going to talk about. First of all, Monte Carlo learning, which in a nutshell we use to mean methods which go all the way to the end of a trajectory and estimate the value by just looking at sample returns. And then we'll talk about another family of methods which also is model-free and can be significantly more efficient in practice, which are temporal difference learning methods. And these are methods which just look one step ahead and then estimate the return after one step. And then what we'll see towards the end of the class is that we can actually unify these approaches, and there's a whole spectrum of methods known as TD lambda, where we can unify and kind of go any number of steps along the trajectory to come up with a viable estimate of what the value function is for our problem. So that's the goal. I anticipate that we will probably get to here, but there's some details which are sort of deferred to an appendix again, which basically give the sort of formal proofs of the equivalence between Monte Carlo learning and TD learning. So that might be left until after this lecture. You can look at it in your own time. Okay, so let's start with the introduction. So let's kind of just take stock of where we're up to so far. So last lecture, we saw in the previous lectures what the definition of a reinforcement learning problem is, and we formalized these environments, a large class of environments, by using a Markov decision process. And then last lecture we saw how to solve a Markov decision process, and by solve we meant find the optimal behavior in that MDP that maximizes the amount of reward that the agent can expect to get from any state in that environment, any state in that MDP. But this was all for a known MDP, so someone had to plug in the dynamics of that MDP and the reward function for that MDP, and then you could use dynamic programming to turn the handle, apply these iterative equations using the Bellman equations, back up those Bellman equations again and again and again, and we could solve it. We could output the optimal value function and hence the optimal policy for that MDP. And what we did last lecture was we broke it down into two pieces. We started off by first of all using dynamic programming to evaluate a policy, and then in the second part of the lecture we saw how to use that as an inner loop, so once we knew how to evaluate a policy we could find the optimal policy. And what we're going to do with model-free methods is we're going to do something similar. We're going to give up on this major assumption, which is that someone tells us how the environment works, which is really unrealistic for most interesting problems. And what we're going to talk about instead is these model-free methods, which go directly from the experience, the interactions of the agent with its environment, directly from those interactions to a value function, and hence a policy. But what we're going to do is, just like in the dynamic programming case, we're going to break it down into two pieces. We're going to break it down into policy evaluation, and then we're going to use our methods for policy evaluation to help us do control. And so what we're going to do is this lecture we're going to focus just on the policy evaluation case. We're just going to look at prediction. We're just going to ask the question, if someone gives us a policy, how much reward will we get for that policy? And we're going to try and figure out how we can do that entirely model-free without anyone telling us the dynamics or the reward function of the environment. So now you can just run your factory and see how much reward you get and estimate the value function directly from just trying things and seeing what happens. And next lecture we'll use these core ideas to actually do control and find the optimal value function and hence the optimal policy for the MDP. Okay, so there's two distinctions we're talking about here. Distinction between planning, which we did in the last lecture with a known model, and this and next lecture we're doing model-free, full reinforcement learning problem, model-free, no one tells us the environment. And the second distinction is between prediction and control, whether we're just evaluating a given policy or whether we're trying to optimize for the best policy. And that's this lecture and the next lecture. Okay? So this lecture, model-free prediction. how to figure out the value function for an unknown MDP when someone gives us the policy. Okay, so now let's talk about our major methods for doing this. You should be thinking, well, how can I do this? How can I figure out the value function when no one even tells me how the world works? But we'll see it's actually straightforward. And our first method is Monte Carlo learning. It's not necessarily the most efficient method, but it's extremely effective and actually very widely used in practice. And the idea is just to learn directly from episodes of experience. So we don't need knowledge of the MDP transitions and rewards, so this is model free. And what we're going to do is look at complete episodes. So this is really suitable for episodic tasks where you start, it's like a game or something. You start at the beginning of your game and you play for some number of steps, and then the episode always finishes, always terminates. And what we're going to do is we're going to go all the way through our episodes, and we're going to use the simplest possible idea to estimate the value function, which is just to take sample returns. So we're going to look at, one episode I got a return of 5, the next episode I got a return of 7, so we can already estimate the value function from our start state as being 6, the average of 5 and 7. So we're going to use the simplest possible idea, which is just to look at sample returns and average over them. And that's Monte Carlo reinforcement learning. Now there's a major caveat here, which is that this only works for episodic MDPs. You have to terminate to be able to form this mean. And we'll see some other issues with Monte Carlo learning, but nevertheless it's such a core idea. I think we should begin there. It helps us to understand the key intuitions, and once you can do Monte Carlo learning, you can build up a value function, you can solve for that value function, you can do all of reinforcement learning with this very simple idea. So let's see how this actually works a little bit more by going slightly more into detail. So what's our goal first of all? So we're going to try and learn this value function, the expected future return from any state. Well, what we're going to do is just observe some episodes of experience under the policy that we're interested in evaluating. So if we want to know what happens following the random policy, just going to have our robot, it's going to wander around randomly for a while. That's one episode. We're going to do another episode. I'm going to wander over here. And then we're going to look at those episodes of experience. We're going to look at the stream of states, actions, rewards that we sampled from our policy and from the environment. And what we're going to look at is the total discounted reward that we got from each time step onwards. Okay, so that's this GT, that was the return. The return was just the reward from that time step onwards until the end of the episode with some discount factor. So this is going to be different for every time step in the episode. The return that I see from the beginning of the episode includes everything all the way along this trajectory, whereas the return from halfway through only includes the rewards from halfway until the end. Okay, and what we're going to do now is we're going to estimate the value function by basically just taking this expectation here. So the value function is the expected return from time t onwards if we were to kind of set our state to that particular point. So if I was to set my state to here and look at the expected return from this point onwards, that's the definition of the value function. So all we do in Monte Carlo policy evaluation, this simplest idea of Monte Carlo learning, is we use the empirical mean return in place of this expected return. So we're just going to replace this expectation with an empirical mean, and we're going to collect as many samples as we can from each of these states of what happens from that point onwards. And then the only issue is how do we do this when we kind of don't get to reset our state back to that exact point repeatedly, and we want to kind of figure this out for all states in our environment. How do we get the mean for all states just from trajectories? And there are two different ways we can do this. And they both work and they're both effective, but there's a sort of subtle difference between them. So the first approach is what's called first visit Monte Carlo policy evaluation. So to understand this, imagine that you've got some loop in your MDP where you come back to the same state repeatedly. But to evaluate a state, what we're going to consider is the very first time we visit that state. We're going to basically say, the first time I get to this state here, in some trajectory, even if I come back to that state later and then go off and get some reward afterwards, we're just going to look at the first time I arrived at that state. And when I reach that state for the first time, I'm going to increment a counter to say how many times I visited that state. And I'm going to add up the total return. And now I could just get the mean return from that state onwards. So we consider, in each episode, we're going to look at the first time I visited that state. We're going to measure the total return we got from that. And we're going to take the mean over those total returns from that point onwards. And all we're going to use is a very simple mathematical result, which is the law of large numbers, which basically says that when you take a mean of a bunch of ID random variables, that the mean of those random variables actually does approach the true expectation. So that tells us that if we see enough episodes, if we just randomly sample enough episodes, this very simple idea of Monte Carlo learning really will converge on the true value function for our policy as we get more and more samples. And the only requirement is that we somehow visit all of these states. And we do that by just sampling along our policy itself. So we generate trajectories along our policy, we do that again and again and again, and we just look at the returns that we get from the first time you visit a state onwards, and we average over those returns. Okay? People understanding? Questions on that? Good. Yeah.
I'm slightly confused because every time we enter the step, we increment the counter, right? Or because if we...
The first time we visit that
so
state.
it will be always one.
No, because the counter persists over multiple episodes. So what we're trying to do is get an average over multiple episodes.
Okay.
So this is counting how many times over a set of episodes, how many times have we visited that particular state for the first time. And this is telling us the total return over many episodes. We're adding on the complete return for each episode here. So this is just a very simple way to say we just take the mean of all of those returns. Okay. Yeah.
If the state space is really large, then the number of episodes you need to run, doesn't that go up exponentially?
No. Well, so first of all, we can ask how quickly does the law of large numbers, basically if you want to know how quickly does it approach the mean, that's the central limit theorem. So we basically know that you normally get some normal distribution, and the rate at which the error reduces roughly sort of with a variance of 1 over n. Okay, so the number of episodes you need to reduce the variance. So the number of visits you need to any individual state is kind of the error you get has a variance which reduces with 1 over n, which is completely independent of the size of the state space. So you just need to see that returns from that state that number of times, and that very quickly will reduce your variance. And the size of the state space, again, the only thing which matters is that we see these states enough times. So each time we're going to see a trajectory, and we basically want to make sure that every state in that trajectory we're maintaining this mean for. So again, as long as your trajectory visits the states that you're interested in, it basically depends on the frequency with which you visit those states. So you have to see those states some number of times, and so it depends on how frequently your policy visits the states that you care about seeing the value function for. But again, that's actually independent of the size of the state space. So that's one of the nice things about these model-free methods, actually, is they don't have, unlike dynamic programming where we're doing full sweeps, we're just sampling here, and sampling actually kind of breaks this dependence on the size of the problem. Okay, so that's first visit Monte Carlo. Let's look at a very subtly different version. Sorry, quick question.
I don't understand how can you make sure that you visit all the states and
Okay. We'll talk about that more next class, so I'm going to defer that question mostly to next class. For now, we're just doing policy evaluation. So all we care about is how good are the states that we visit under policy pi, and the way that we make sure that we see all the states that we care about under policy pi is by following policy pi. So just by following the policy that I'm trying to evaluate, we guarantee that we see all of the states that are reachable under that policy. And so we will see all of those states. And that idea is sufficient for now to make sure that we see enough visits to all of those states. In subsequent lectures, your question's really actually a very interesting one, which is how do you make sure that you cover the whole state space when you're trying to find the best policy? And that's a whole issue of exploration that comes up in reinforcement learning. It's one of the fundamental questions of reinforcement learning. But here we're just trying to evaluate this policy, so it's enough to just run episodes with that policy. If I want to know what happens if I follow a straight line to the wall, all I need to do is just keep following that policy of running a straight line towards the wall, and I'll see all of the states which are of interest, and I can evaluate those states because I've run that policy already. Okay, second idea, very closely related, is every visit Monte Carlo policy evaluation. So now to evaluate a single state S, if we've got this loop again, the only difference is now that we're going to consider every visit to that state instead of just the first one. So we're basically going to come around, and if I could do my loop, I'm going to come back to it again, and I'm going to include both my original estimate of the return, including the loop, and also my second estimate from that state the second time I visited to it. So basically, in one episode, you can increment the counter multiple times for this state. Each time you visit it, you'll increment the counter, and you'll add on a different value of the return based on the point which you were up to at that time step t for each of those visits. Apart from that, the algorithm's identical. We still can use the law of large numbers. This thing still finds the true value function. Everything's good. So both of these are valid estimators of the mean, of the expectation, by just taking samples of the mean in different ways. Yeah.
Are there any intuitions which one is better, and in which case which one should use?
So it sort of depends on the setting. Actually, when we talk about TD lambda, I'll come back to that question, that there's different types of traces you can use, and they correspond to every visit and first visit traces. And there's some evidence in favour of both, depending on the domain, actually. Okay, so let's make an example. So I just want to talk about this. It's a little bit related to the assignment. So so the idea is we're going to consider, how can I train you up to go and break the casino like after this class? Don't hold me to that. I don't want to be responsible for anyone losing money. Casinos actually don't follow exactly this. Is a simplified version of blackjack, so you won't be able to use this and really win money. But we're going to consider the game of blackjack, sometimes called 21 or pontoon, things like that. And it's a very simple game where the dealer basically you get dealt. You start off with 2 cards, and the idea is to get as close as possible to 21 in the sum of those 2 cards without going over 21. So you just add up the face values of all of your cards, and if you ever get dealt a card such that the sum of your cards goes over 21, you're bust and you lose. But the closer you get to 21, the more likely you are to beat the dealer, who also has 2 cards, and is going to play the game the same way. And if your total beats the dealer, then you win the game and you win some money. Okay, so that's the game of blackjack. And how many people know the game, by the way? Good, yeah. Okay. So the way we're going to represent this, we're going to represent it as an MDP, and we're going to treat the state as having basically 3 different variables in the state space. First variable is the current sum of our cards. So if we've got 3 cards and the sum of those cards is 17, we're going to say we're in a state with a sum of 17. And note that we're not going to consider sums below 11, because for those states we're just going to automatically ask for another card. Because for free you can ask for another card, and it's not an interesting decision at that point. If you have less than 12, there's no interesting decision to make, because you'll always ask for another card. Okay, so we're only going to consider the states where we actually have an interesting decision to make, where the sum of our cards is between 12 and 21. And we're going to look at what the dealer's showing. So when you're playing your game, you see one card of the dealer's, and that you can use that to decide whether you should ask for another card or not. And your goal is to, without having seen the dealer's next card, how can you decide on this decision of whether to ask for another card and possibly go bust, or to stick with what you have. So you've got those 2 actions, to stop, stick, or to twist. And if you do stick, then the dealer plays out the game. You just think of that as the turn of the environment. The dealer plays out the game all the way to the end. That's like one step of the environment. And then you get +1 reward if your sum's greater than the dealer's sum, 0 if it matches, and -1 if you've got less. And if you twist, then you get -1 if you go over 21, because you go bust, and 0 otherwise. And for the transition structure of this MDP, the only thing we're going to add to it is this idea that if you've got less than 12, we're going to automatically twist. So we're not going to, that's just part of the MDP then. So you only actually make actions where there's an interesting action to make. And there's this sort of auto twist as part of the environment if you have less than 12. Okay, so let's apply Monte Carlo policy evaluation to this problem. And so next class we'll actually see how to really find the optimal policy. For now we're just doing policy evaluation. And what we're going to do is we're going to choose a really naive policy, and we're going to see what happens with that naive policy. And so the policy is going to be, we're going to stick if the sum of our cards is 20 or 21. And otherwise we're always going to twist. So even if we've got 19 or 18, we're just going to twist. And we want to know, well, how good or bad is this? And we're going to consider, oh sorry, I forgot to mention one more state variable. So we have 3 state variables. The third state variable is whether we have an ace in our hand, which is usable. That means it can either take the value of 1 or 11. And so it's good to have an ace in your hand. And basically, what we see is that this is basically using, I think, every visit Monte Carlo learning. And what was done here was basically to just roll out 10,000 episodes of blackjack. So to literally play out this game with 10,000 hands and then 500,000 hands and apply exactly the procedure we've just seen. So for these 10,000 hands, every time we came across one of those states, every time we had a sum of 13 and we had a usable ace, and the dealer was showing a 5 or whatever, we would find the appropriate point here in the value function space, and we would update that estimate of the value function a little bit towards the mean of. So for each point here, we're keeping a separate estimate of the mean for that state. And so for all of these states, we update the mean from these episodes, and if you run enough episodes, you start to get the shape of the value function. And what you should immediately see here, this is really to give you a flavor of what happens with these algorithms. You see that even after 10,000 episodes, you still have you get a pretty decent estimate of the case where you don't have an ace, but the estimate where you do have an ace is much noisier, and that's because these are rarer. These states are rarer. So 10,000 episodes, you don't actually see enough cases where you've got an ace to really figure out all of these means correctly. So it's still quite noisy, and you need something like 500,000 episodes to really get the correct shape of this value function. And this shape is telling you something quite interesting, which is, as you'd expect, if the dealer's showing something towards an ace, so the better the dealer has, the worse off your value is. Unless he's got an ace, that's even worse there. And this is your sum. So if you've got 20 or 21, you do quite well in this game. But for anything below that, you do really badly because you've got this very naive policy where you're just going to keep twisting and probably go bust. So we see that emerging nicely from the structure of this value function, just by sampling. So no one told us the dynamics of the game. No one told us the probabilities that govern the game of blackjack. No one told us the structure of the pack, the deck of cards. This was just by running episodes, trial and error learning, and figuring out the value function directly from experience. Okay?
Can you just clarify the dealer answers? Does it go ace, 2, 3, 4, all the way up to 10?
Yes, yeah. Okay?
What about Jack or Queen?
Okay, so Jack, Queen, so picture cards are just treated as 10s in this game. So in blackjack, all picture cards have a value of 10. Yeah, question?
So what, this is showing the expected reward given that you're at that state if you follow the policy?
The expected return, which is,
Yeah.
the expected return, which is the value function.
Yeah.
So if you were to follow this policy, each point on this diagram, the height of this point on that diagram is showing you your estimated value function, your estimate of how well you will do, of whether you'll win or lose this game. If you're in a situation where you say, where the dealer is showing an ace, and you've got a player sum of, say, 19, this value here tells you how well you think you will do in that game. And so it's the shape of this value function is exactly the information we're after. Like once we have this, we can do all kinds of things. Like the key quantity we're after is this picture. Once you have this picture, you can evaluate your decisions and pick the best decision and make better policies because you can look at the shape of this surface for all different policies and find the best one. Okay. Good. And so the assignment is to work on a similar game, something called Easy 21, which I think you'll have fun just playing around with and trying to understand. And you can run all kinds of reinforcement learning algorithms to figure out not just policy evaluation, but to find the optimal policy for that game.
Does that value function tail off slightly with the 10 compared to the 9 on the bottom right-hand side there?
Yes.
I don't understand why it would do that.
It might just be noise in the evaluation, I would
Well,
guess.
the 10 would be a better estimate, right? Just because you have more 10s. If you bundle up together all the jacks and queens and kings, or it, maybe not better, but different. Sort of.
But if the dealer's got a 10, it's a better hand for the dealer, right? That's why you get the worst return.
No, because you're on 19. When you're on 19, you don't want to get a 10. That's why it's improving slightly all the way up, because you don't want large cards. So you're happy when the dealer's got large cards.
Well, it's a little bit unclear, right? So it depends on the strategy the dealer's using to twist, actually. Right. So I think it depends. So it might be that the dealer has the same strategy as us, in which case having something like a 7 or 8 is actually a bad situation for the dealer, because they will probably twist and most likely get a 10 again, and then they'll most likely twist again, and and there's a higher probability of going bust here than if they've already got a 10, in which case they're likely to get another 10 because there's more of them, and then they'll stick. So I think it depends on the dealer's strategy.
So to program this, you actually have to program the dealer strategy as well, which we don't know.
You do know for the assignment. Okay. So let's move on. But I think that illustrates that the value function depends on all kinds of factors. Like the actual value function does depend on every aspect of the environment. It depends on how the dealer acts. It depends on the deck of the card, the randomness, how many 10s there are compared to 9s and 8s. All these things affects the value function, and yet we don't need to tell our agent any of those things. Just by sampling the returns, we're able to go directly to the right thing, which is the value function, and hence the optimal behavior in the next lecture, without needing to explain anything about the dynamics. And that's the power of model-free reinforcement learning, that you can go directly to the result without going through these intermediate steps. Okay, so far we've talked about this sort of explicit computation of the mean. So what we're going to see is that this can be done incrementally. We're going to start to move towards online algorithms, which step-by-step update the mean. So this slide is it's probably a well-known result. Sorry if you guys are aware of this, but it's just to show that the mean can be computed incrementally. You don't have to, first of all, make the sum of everything and then divide the sum by your count. You can do it incrementally. And so very briefly, if the mean of k elements is just 1 over k of the sum of those elements, what we can do is we can split this sum out into a sum up to k minus 1, so the previous k minus 1 elements plus the kth element. And then what we can do is just observe that this sum here is k minus 1 times the mean up to k minus 1. So this sum here is just, you can take your previous mean, multiply it by k minus 1, and then add on your new element, and divide by k again. That gives you your new mean. And then if we just rearrange these terms, we see that if we collect together our xk's, then we've got 1 over k of them here, and our mu k's we can basically pull out here, and we can subtract off the 1 over k mu k that we have here, and this is the k times 1 over k of mu k that we pull out here. And what we see is that you can basically, the new mean is the old mean plus some step size, 1 over k, a little increment towards the difference between your new element and what you thought the mean was. So we're going to see a lot of algorithms which take this form. There's an error term here. So think of this error term as this being your estimate of what the value is going to be. Before you actually see this new element, you've got some estimate of what you think that value is going to be, which is your previous mean. So you think that your elements are going to have this value on average. Then you see your new element here, and there's some kind of error between what you thought was going to happen and what actually happened. So that's your error term here. And now what we basically do is we update our mean a little bit in the direction of that error. We're going to see a lot of algorithms which take that form, where you sort of correct, you have like a prediction, and you correct that prediction in the direction of the error. So basically, if you were estimating your mean too low, and you see something higher, then you need to increase the value of your mean in the direction of the error between what you thought the mean was and what you actually observed. So that's the idea of these incremental mean computations. And we'll pretty much see that every algorithm in the remainder of this lecture takes this form. And so let's first of all do this with incremental Monte Carlo updates. So we're going to take our Monte Carlo algorithm and we're just going to make it an incremental update. So we're going to do it episode by episode now, without keeping track of these sums and these visit counts. You still need the visit count, but without keeping track of the sum. What we're going to do is we're going to take the same algorithm, so for each state with some return that we've seen. So for now, we'll just keep the visit count. And what we'll do is we'll update every time we see that state. We're going to measure the return from that state onwards. And we're going to look at the error between the value function, that's what we thought the return was going to be, and the return we actually observed. We're going to generate some error. We're going to update our mean estimate for that state a little bit in the direction of that return. Okay? And so this is exactly the same. We've just transformed our computation of the mean in this way. Yeah, question?
In the example, you put the return in the end, you didn't have the intermediate return. And here you have intermediate return.
No, no. So we're not computing intermediate returns. That's the next part of the class, actually. So I'm glad you said that. So what we're doing is we're still getting the complete return, but it's only incremental in the sense that every episode we're going to update our mean, and just it's a trivial rewrite of how we compute the mean. And the reason we're doing it this way is we're showing how this is going to develop towards other algorithms. So we're going to replace this 1 over n by other quantities, and we're going to replace the target we move by other quantities. But it's just to show that, so we're doing exactly the same computation as before. Nothing has changed. It's just an incremental mean update, just to put things in the form that we're going to use later. So we're doing things episode by episode. We're incrementally updating our estimate of the mean for that. Yeah.
But we add these values after we finish the episode, right? Because then we know the whole value function for this step.
Yes. So this is all forward-looking. Everything with Monte Carlo so far, you have to wait until the end of the episode to see the return that you got, and then you have to go back to the state that you want to update and say, okay, well, from that state, I ended up getting 100 points.